Hi, welcome back to the lecture series on microeconomics. Earlier we have discussed the theoretical Cournot and Stackelberg models, and we have found the Farm's equilibriums in those cases. Now we are going to revisit those oligopoly or duopoly models through a numerical exercise. I hope that this numerical illustration will help you to understand the working of these two models. So, first let us write down the functions which are common to both the models. So, we start with a market demand function which is inverse demand function, and capital Q is basically the sum total of output being produced and supplied by these two firms 1 and 2 respectively. Okay. And then we also assume that the cost structure is different for these two duopolist firms. So, the cost function for the first firm or duopolist 1 is basically given as 5 times Q1, and the cost function for the firm 2 or duopolist 2 is given by 0.5 times Q2 square, right. So, I must say that these are all hypothetical numbers. So, if you change these numbers, of course, you expect a different solution, right. So, let us going to look at how with this common information we can derive the Cournot equilibrium and Stackelberg equilibrium, right. So, let us first study the case of the Cournot equilibrium. Okay. The Cournot model case. So, how to solve a Cournot model? We have to proceed step by step. So, step 1 would be writing the profit function for both firms, and if we do so, let us start with firm 1. So, it is going to be the revenue earned by the first firm and the cost incurred by the first firm, right, and then we get 100 times Q1 minus Q1 times Q1 plus Q2 minus 5 times Q1, right. Okay. Similarly, one can write the profit expression for the duopolist 2 or firm 2, and that would be so, I hope that you can see the interdependence between these two duopolist profit levels, because note in profit function 1 Q2 is present and in profit function 2 Q1 is present, right. Okay. So, now what would be my second step? So, I hope you remember that its reaction function, which is basically the most important concept in a Cournot duopoly and Stackelberg duopoly model in order to solve these models. So, we have to derive the reaction functions. From where to get the reaction functions? We have to find out the first order conditions, right. And let me now find out the first order condition for firm 1. Okay. And if I now express Q1 in terms of Q2, then what do we get? We get basically the reaction function for farm 1, which is given by R 1. Okay. So, similarly I can take derivative of the profit function with respect to my output for farm 2 and output from farm 2, and if we do so we get 100 minus q1 minus 3 q2, and that shall be equal to 0 as well. And if now I express the q2 as a function of q1, then I get right. And if you remember the theoretical discussion that we had earlier, this is the reaction function 2. Okay. Now we move on to step 3, and in step 3 let me tell you that this is an optional one. Because now from this step 2 you can solve this Cournot model in two ways, one is through the graphical approach and the other through the algebra, right. So, I will show you both. So, the first one is basically the graphical approach, which is kind of optional, but let us have a look at the graph of the reaction functions, right. So, we have to basically draw the reaction function for both the duopolists, right. So, if we now draw graph, so two farms output levels are measured along different axes. So, let me assume that this is 100, and similarly I can also assume here this as 100. Basically I am trying to get the intercepts properly plotted, so that these two reaction functions can intersect as they should be. So, now this is more or less half. So, 50, let me mark this, and this is almost 1/3 of the distance. So, this is kind of, this is very close to 33.3. Okay. Okay. So, now we are ready to draw the reaction functions. So, to plot the reaction functions, let us first look at the reaction function of farm 1. So, that comes from this first order condition, and if I want to plot that, then I am going to get q1 value close to 47.5, which can be here, and the corresponding q2 value would be 0, and if I now plug the value q1 equal to 0, then q2 takes the value 95, right. So, somewhere here, right. Okay. Okay. So, now if I join these two points, I get my reaction function 1, or the reaction function of duopolist 1, right. Okay. So, now to find the reaction function of duopolist 2, we follow the same procedure. We now have a look at the reaction function 2, which comes from this first order condition, and if I now assume q2 equal to 0, then I get q1 equal to 100, and if I assume q1 equal to 0, then I get q2 equal to 33.3. So, if I now join these two points, these are the basically intercepts of the reaction function 2, or the reaction function of duopolist 2. So, I get the second reaction function as well. Okay. So, we know from our theoretical discussion that it is the intersection point of these two reaction functions where the Cournot equilibrium is going to be determined, right. So, one can read from graph that it is going to be close to 20 and it is going to be close to 40, but let us find the exact numbers, right. So, then basically I move to this step number 4, which is basically finding the exact value of the coordinate of the Cournot equilibrium, right. So, the step 4 would be algebraic solution of the Cournot duopoly model, and for that basically we have to use these reaction functions only. Basically, we have to find the solution of these two first order conditions which leads to the reaction function. So, basically we are after finding the intersection point of two reaction functions, right. So, note that I can write this, and from here I get Q2 star equal to 21, right, and as I have solved Q2 star, I can plug the value of Q2 star in the expression and we get Q1 star equals so this actually is coming from the first order condition 2. Okay. So, now the other part of the solution is to find the price. Now, as opposed to a discriminating monopolist model, there will be only one price in the Cournot equilibrium model, and how to get that price. So, for that we have to use the market demand equation. So, we need to plug the values, optimal values of Q1 and Q2 into the demand function, and if we do so, we basically get a price equal to 42. Okay. Now, next step would be to compute the profit, and this is required if we want to compare the Cournot model outcome with Stackelberg model outcome. Okay. So, now let us look at the profit expressions for individual firms. So, we have R1 minus C1, and that is if I plug the values of price and quantities in proper places, then I get some number, and similarly pi 2 I get revenue minus cost, and again if I write down the proper numbers in proper places, then I get this expression, and if I compute I get a number approximately this. So, finally, we have obtained the Cournot model outcome, and now we are going to look at the Stackelberg case. Now, in the case of Stackelberg, we have to assume that one firm is a leader and the other firm is a follower. Now, without losing anything, we can assume that our duopolist 1 or firm 1 is the leader and the other firm 2 is a follower. If we assume that, then let us see how the model outcome is going to respond to that assumption. So, Stackelberg model, right. So, let me write down explicitly the assumption we are making. So, we are making the assumption that our farm 1 is leader and farm 2 is follower. Okay. So, we know that in that case what we have to do? The farm 1 actually knows the reaction function of the farm 2 as it is the leader in the market. So, the farm 1 will now substitute the opponent farm's reaction function, which is R2 that we have just derived, in profit function, right. Okay. So, here let us start with the profit function of farm 1 or the leader itself. So, we have this profit function from our previous derivations. Note that we are not changing any functions from the Cournot model, so that we can compare two model outcomes. Actually, we are going to show that the Stackelberg model produces higher profit for the leaders, that is our objective to show actually. So, now let us plug the reaction function expression R2 in the profit expression of farm 1, and that is basically the expression for Q2, right. Okay. So, now let us substitute that here. So, that is this expression, right. Okay. Now, we get a final expression of profit like this. Okay. Now, we know what to do from our theoretical discussion. Now, the Stackelberg leader will behave like a monopoly and it will try to maximize its profit, and now for that he can take the derivative of the profit function and we get right. So, this first order condition for profit maximization gives us a number which is approximately equal to this, right. So, now if I plug back that value of Q1, I get the maximized profit, and which is coming out to be around this. Okay. So, now we know that our farm 2 is a follower. So, that poor fellow has nothing to do but substitute this output level that the market leader has already set in the market in its reaction function and get his optimal output level in response. So, our follower or farm 2 will substitute optimal output level of leader, which is Q1 star, in its reaction function, which is R2, right. So, if it does so, then basically it gets an output level which is approximately equal to this. Okay. So, correspondingly we can look at the optimized profit for farm 2. So, farm 2 has a profit expression right. So, now you need to plug these optimal values, right, and if you do so, then you get some number again approximately close to this. So, you can see here that if farm 1 behaves like a Stackelberg leader, its profit is much higher than compared to the Stackelberg follower duopoly farm. Now, note that when we have derived the Stackelberg solution, in the theory class I probably forgot to mention about the conjectural variation in the case of Stackelberg model, but here we have some time to discuss that. So, note that in the Stackelberg model case, actually the conjectural variation of the leader farm is equal to the slope of the reaction function of the follower farm. Why? Because the leader farm actually is substituting the reaction function into its profit equation, right. So, the leader farm actually has some guess about the behavior of the follower farm, and that is exactly given by the slope of the reaction function of the follower farm or farm 2. What does that give? That gives that if there is a change in the farm 1's output, then how farm 2 is going to change its own output, so that it maximizes its own profit. Okay, so, we have obtained our Stackelberg model equilibrium. Now, in the remaining time we could also explore the solution of the collusive duopoly model. What if there is no leader, there is no follower, these two duopolist firms decide to cooperate with each other, and if they decide to make a team, then they will become a monopolist in the market, and then they will set a new market output level, and how to find that we can see through our numerical example. So, we will now discuss the solution for cartel model, and that is basically the case of joint profit maximization. Okay. So, we will first write down the joint profit equation. So, we will write 100 minus Q1 plus Q2, that is the demand function or price, then we multiply that with the industry supply, which is Q1 plus Q2, supply from both the duopolist firms, then cost shall be deducted 5 Q1 for first firm and then 0.5 Q2 square for the second firm, right. So, finally, what do we get? We get a simplified expression which has 100 q1 plus q2 minus q1 plus q2 square minus 5 q1 minus 0.5 q2 square. Okay. So, now from the lecture on cartel we know how to proceed. We have to find out the individual firms profit maximizing first order conditions. So, basically we have to find out the first order condition by setting this derivative expression to 0, and then if we do so, then I get the optimal value of firm 1's production, but note that here that will be a function of the output level of firm 2, right. So, then basically I have to take another derivative, set that equal to 0, and then I get q star 2, that is going to be a function of q1. Okay, fine. So, now let me name this equation. So, let me say this is my equation number 1, this is my equation number 2. Okay. Now, we know that in the cartel case the equilibrium condition is basically marginal revenue equal to marginal cost equal to marginal cost of second firm. So, basically this is my first order condition. Okay. So, I can substitute 2 into 1 and I get q1 is equal to okay. So, now I get everything in terms of q1. So, from here I can easily solve for q1 value. So, I get q1 star equal to 8.5, right. Okay. Then I can plug this value of q1 star in equation 2, so that I can solve for q2 star, and if I do so I get q2 star equal to 39. Okay. So, then basically I need to plug this q1 star and q2 star values in my demand function, and if I do so I get my price to be set in the market, and I get 100 minus 47.5, which is equal to 52.5 in terms of either rupee or dollar, whatever monetary unit I am assuming for price. Okay. So, then from here the calculation of profit becomes quite straightforward. So, and we can also find out pi 2 similarly. Okay. So, these are basically the individual firms profits. So, with this illustration we come to an end of our discussions on oligopoly models. So, now we are going to enter into the discussions on externality. All of us are aware of environmental issues around us, and now we are going to see how microeconomic theory on externality can be helpful to model environmental problems that we see around us. So, next we are going to discuss the applications of microeconomic theory to model environmental problems.